All right. Welcome to Lecture 14 in Topology on compact spaces. I have 20 minutes. A topological space is compact if any cover of the space admits a finite subcover. Any open cover of the space admits a finite subcover. A subspace of a topological space is compact if it is compact for the induced subspace topology. Equivalently, a subspace K of X is compact if for any family A of open sets in X, which contains K, there exist finitely many sets in the family for which those sets form a cover of K. All right. So let's see here, an example to get us started. Not everything that we know and love is compact. All right, compact is it's a special condition. Certainly, Rn is not compact, and well, here's an open cover. If we take the union of balls of integer radius, positive integer radius, like this, my sad picture of it. All right, clearly the union of all these gets you all of Rn, right? And there does not exist a finite subcover, because if there did, there'd have to be a sort of largest m in the finite subcover, and for the largest choice of m, the largest radius, that would contain all the other balls, right? And then if this is really a cover, then that means that the union of everything in the cover gives you Rn, which would mean that Rn is a ball of finite radius, which, to quote my community college professor, this dog does not hunt. So anyway, yeah, Rn is not compact. And that is also true and that's true in any dimension. That argument works for n equals 1, n equals 2, n equals 3, whatever. Any finite set, on the other hand, is compact. Given any open cover, we can simply select the singleton cover, right? And moreover, a discrete topological space is compact if and only if it's finite. All right. So compactness is some kind of like finiteness condition. Think of it that way. That's what my brother always said. He says, when you think of finite, when you think of compact, just think finite. Compact is a way of capturing some kind of finiteness about what you're talking about. So let's see here. F, a continuous map, X, a compact, the compact domain, then the range is a compact subspace of Y. All right, so pick a family of open sets in Y which covers the range. Look at the inverse image of that cover, right? The inverse image of that cover gives you an open cover of the domain, which means by compactness of X, there's a finite subcover, and consequently, the image of that subcover gives you a finite, like F of this gives you that, and that's a finite subcover of the original open cover in Y, which then proves that Y is compact. Excuse me, it proves that the range is compact, I should say. Okay. Of course, you could have the situation where F is not onto, right? You could have that the range is like 0 to 1, but the codomain is like all of R. That could happen, that kind of thing. So just because the range is compact doesn't mean that the codomain is compact for sure. The closed interval 0 to 1 is compact in R. Now, this is a little bit technical. Let's get into it. So let A be a family of open subsets of R which covers 0 to 1. Define X from 0 to infinity to be the set of points T such that 0 to T is a subset of the union over A, finitely many A in the cover. All right, this is a very sneaky step. Notice that 0, 0 equals to 0. That's a subset of A for some A, as A covers 0 to 1. Therefore, zeros in X. All right, and the definition of X here is rather conniving. So if you define B to be the lub of X, the least upper bound, also known as the supremum of X, and if B is greater than 1, that means there exists a T in X such that 1 is less than or equal to T is less than or equal to B, and 0, 1 is a subset of 0 to T, which is and as such, lo and behold, we got it. Then that means 0, 1 is covered by a finite collection of the open sets in the open cover, right? Yay, we win. So what's the other possibility? The other possibility is that b is less than or equal to 1. If b is less than or equal to 1, we're going to get a contradiction. How are we going to get that contradiction? Well, let's see. If b is less than or equal to 1, that means there exists an A such that b is an element of A, and since A is open, there's a delta for which b minus delta to b plus delta is a subset of A, right? Fair enough. However, by the properties of supremum, there exists a T between b and b minus delta, because that's how the supremum works. And great. So then 0 to t is contained in a finite union of the covering sets, like so. But, all right, well, 0 to t, union of subset of some union a1 through an. But notice that if 0 is less than or equal to h less than or delta, then 0 b plus h, which is, by the way, 0 to t union t to b plus h, is a subset of 0 to t union with b minus delta to b plus delta, which is, by the way, a subset of this guy. Uh-oh. Thus, b plus h is an element of x, and that's true for any h in 0 to delta. Well, that's embarrassing because b was supposed to be the supremum. We just found something bigger than the supremum in the set. Not a good look for Mr. B. Not a good look at all. So that's a contradiction, and as such, we have proved that the interval from 0 to 1 is compact. Compactness is preserved by homeomorphism. So if x and y are homeomorphic, then that means there's a continuous bijection, f to y with continuous inverse, f inverse from y to x. And then from the theorem on page 2 applies because f of x equals to y in this context, so x compact implies y compact, right? And vice versa. So it's if and only if here. In other words, compactness is preserved by homeomorphism. So among other things, this means that R cannot be homeomorphic to 0, 1 because 0, 1 is compact, whereas R is not. That was example 1. Proposition. Any closed subspace of a compact space is compact. Number 1. Number 2, moreover, finite unions of compact subspaces are compact. Ooh. All right, let's get to it. How's that go? Well, number 1, suppose Y is a closed subspace of a compact space. We seek to show it is compact, yes? So suppose Y is covered by some open cover, all right? Then, lo and behold, the union of the, if we take the open cover and tack on the complement of x by y, well, that's an open cover of x because, you know, A covered all of y, and of course x minus y covers everything that's not in y, so that's definitely a cover of x. And if it's an open cover of x, and we know that x is compact, well, that means there exists a finite subcover, a1 through an. And of course, if you think about that, I mean, I'm not saying that the finite subcover is a1 through an. I'm saying the finite subcover has to have the form like this because there's no way you can cover the things outside of y except for with this set. So you're forced to put the complement of x by y in that finite subcover. Anyway, and as such, this means that y is, of course, a subset of the union of a1 through an. Therefore, y is compact, as we've shown that an arbitrary open cover of y contains a finite subcover. Woohoo! Number 2, let k1 through kn be compact subspaces of x. Suppose A is an open cover of the union of k1 through kn. Okay, so for any h equals 1 through n, there exists a finite a sub h subset of A that covers k sub h, which is compact. And then k equal to the union of k1 through kn will be a subset of this union over A, where A is taken from the union of these as I say down here, the finite subcover of K is formed by taking the union of finitely many finite covers of K sub I. So, all right, there you go. Finite unions of compact subspaces are compact. Actually, this is one of those few things, like, I feel like I probably could have proved this by myself just thinking about it for a few minutes, you know? Like, I think you can prove number 2 if you just sit and stare at it and scratch your head for a minute and think you'll get it. That's not bad. All right, number 4, page 4. A subspace of X, rather a subspace, let me get it here. A subspace in R is compact if and only if it is closed and bounded. Corollary. Lemma. Homeomorphism preserves compactness. All right. Didn't I already prove that? I already proved that. I proved compactness is preserved by homeomorphism. Back to page 3. Why am I saying discuss it, lemma? Man, I must have started writing this after I wrote the other page, like a day or something. Oh well. Proof. Let A be a subset of R closed and bounded. Then A is a subset of minus A to A for some A, because boundedness means that you can fit it inside some, sufficiently large open ball. And well, anyway, it means boundedness in R can be taken to mean that you can fit the set inside the subset of inside a closed set of the form minus A to A. All right. You could define boundedness of a set in terms of that if you wanted. I don't know what your definition of boundedness was for a subset of reals, and I've forgotten what our definition was. Maybe this is it. Certainly, whatever your definition of boundedness is, you can get this from that for reals. For reals. I'm sorry for that. Anyway, but minus A to A is homeomorphic to 0 to 1, and as such, it's compact, which implies then that A is compact, since it's a subset of a compact space. All right. And, well, it's a closed subset of a compact set, and then we can use the previous proposition from page 3. Conversely, because that was any closed, proposition number 1 of page 3 was any closed subspace of a compact space is compact, so yeah. Conversely, if A, a subset of R, is compact, then this covers A. Hence, there exists a finite subcover, and as such, it's bounded, because you can just take from this finite subcover the biggest, baddest one of those, the max, and there you go. You got it bounded. That's not bad. That's not bad. Cool. Finally, if P is not an element, well, I'm not sure what we're after here. Let's read. I thought we were done. I'm a little bit uncertain why we're doing what we're doing here, right now, to be honest with you guys. Finally, if P is not an element of A, all right. What's P? Why are we looking at P? Well, anyway, if P is not an element of A, then certainly f of x equals 1 over x minus P is continuous on the reals with P removed. Hence, f of A is compact, because the continuous image of compact is compact, and thus bounded. Thus, P is not an element of the closure of A, and hence A is closed. Oh, okay, I see. I'm sorry. We need to prove A is closed. I got sucked in. I lost track. We proved it's bounded, but we hadn't proved it's closed yet, so this little argument here proves A is closed. Lovely. Corollary. Let X be a compact topological space. Any continuous function from X to R has a max-min. This is sometimes called the extreme value theorem. And here's the sketch of the proof. Note f of X is compact in R. And so that means f of X is closed and bounded. But if f of X is a subset of R is closed and bounded, that means that it has max-min points. All right. And again, I think we're drinking from the well of real analysis here a little bit, in terms of claiming closed implies the max-mins are realized. Have we proved that in here? I'm not so sure we proved that. You correct me in the comments if I'm wrong. Number 5, theorem. Consider a closed map with Y compact, and the image of every fiber is compact also. then X is compact. All right, so if you have you're mapping to a compact space, and every fiber of your map is compact, then the domain must also be compact. All right, and this is intuitively I think this is intuitively natural because if you just think about the domain, you can cover the domain with the fibers, like the domain, the fibers form a partition of the domain. The fiber partition, by fiber equivalence, the partition of the domain, 2 points are equivalent if and only if they're in the same fiber, which means they map to the same point in the range. Anyway, here let's look at the argument. But he says without loss of generality, you can assume that f of x is equal to y. So if the map was not onto, then if you think about it, it's fairly clear that the subspace of the codomain, which is the range, would also be compact, given that y is compact. It's pretty easy to see that. So there's not really any loss of generality here. And he defines this A prime gadget. He says A prime is y and y such that the inverse image of y is a subset of A. So this is the set of points. How to say this? It's all the y's which are getting mapped to I'm having trouble how to verbalize this. The fiber of y is a subset of A, right? So y in the range such that the inverse image of y is a subset of this given A. This is what A prime is. All right, sorry, I don't have good words to say what that is. I mean, it is what it is, but anyway, it says define that. Then, if you look at it, y minus A prime, so the complement of y by A prime is actually the image, it's the image of the complement of x by A. And so that means then, if you think about it, if A is open, x minus A is closed, and if f is a closed map, then f of x minus A is closed, and if that's the case, then this y minus A prime, which is equal to f of x minus A, is in fact closed. And if this is closed, then that implies that A prime is open. All right, great. Okay, fine. So let A be a open cover of X, and let B be a family of finite unions of elements of A. Then we can form B prime using this prime notation we introduced up there. That is going to be an open cover of Y. And if y is an element of y, then f inverse of y, of course, is compact, which means that there exists a finite collection of A1 through AM and A that cover that fiber. And since y is an element of this B prime, for B equals to the union of these A's, and that means, well, okay, that is what it is. However, as y is compact, we have a finite sequence of b1 through bn in B, such that y is the union of these b1 prime, b2 prime, bn prime, and x is then the union of the corresponding b1s through bn. And as every b sub I is a finite union of sets in A, we find a finite subcover for A by collecting such sets. So I think all this is really doing is running through, making precise the intuition I said at the start, which is that, X is the union of the fibers, and if each fiber is compact, you can use that finiteness for each fiber to pick out, a finite collection of things, and then you have to play the inverse image game to get it to come back, and this is what it looks like. So anyway, that's that theorem. But we may have occasion to use these theorems, so we should try to keep them in mind, all right? Let B be a basis for space X if every cover of X is made by elements of B, has a finite subcover, then X is compact. Okay, and then finally, Let K1 through K2 through da 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 be a countable descending chain of non-empty closed and compact sets. Then the intersection of all of them has to be non-empty. This, I think, ultimately gives us some fixed point theorems. But anyway, the proof of these are on Minetti on page 75. And I believe my fish sticks are ready. I must go. Thanks, guys.